All right, today we're going to do something really cool. We're going to make the invisible visible. We're diving into a concept that's basically a map for the unseen world of electricity. It gives us a way to actually visualize the forces that are all around us all the time.
You know, if you've ever looked at a hiking map, you've seen those squiggly topographical lines, right? Well, those lines connect all the points that are at the exact same elevation. If you walk along one, you're not going uphill or downhill, you're on flat ground. So here's the big question. What if we could draw a map just like that, but for the invisible world of electricity? A map of equal electrical height.
Well, it turns out we absolutely can. And this map for electricity has a name. It's called an equipotential surface. And really, it is the exact same idea as a contour line on a map. Every single point on one of these surfaces has the exact same amount of electric potential.
Okay, so let's put a formal definition on this. An equipotential surface is just a three-dimensional surface where the electric potential, we call it V, is the same at every single point. That's it. You can think of it like a landscape of energy, and on one of these surfaces, the height is the same no matter where you stand.
Okay, now let's have a little fun with this. I've got a puzzle for you. Check this out. We've got 4 different situations where a positive charge is moved from point A to point B. Just take a look. Notice how the paths are all different, and the equipotential lines look a bit different in each one too.
So here's the question. In which of these 4 scenarios do you think it takes the most work to move that charge from A to B? Is it the straight shot? The long, wavy path? What do you think? Take a second and make a guess.
Okay, you ready? The answer is, it's a trick question. The work done is exactly the same in all 4 cases. Crazy, right? But here's why. The work it takes to move a charge in an electric field only depends on the potential at the start and the potential at the end. And if you look closely, in every single one of these pictures, the charge starts at a 20-volt line and ends at a 40-volt line. The path it takes to get there, totally, completely irrelevant.
And this is the most important takeaway. If work only depends on the change in potential, then what happens if there's no change at all? Right. 0 work is done. Moving the charge along an equal potential surface is the electrical version of walking on perfectly flat ground. You're not fighting against the field, not one bit.
Okay, so we know what these things do, but what do they actually look like in the real world? Let's check out the 3 most common shapes you're going to see. First up, we have the simplest one, a single point charge. It's just sitting there in space. The potential radiates out from it equally in all directions, which creates these perfect concentric spheres. It's just like the ripples spreading out when you drop a pebble in a pond. And just like those ripples, the potential gets weaker and weaker the farther away you get.
Okay, next up, what if instead of a point, you have a long, straight line of charge? Think of it like a charged wire. What happens then? Well, the potential radiates outwards from the wire to form a series of nested cylinders, kind of like Russian dolls, all centered right on that wire.
And for our last shape, what if you have a giant flat sheet that's all charged up? This one's super simple. It creates these perfectly flat equipotential surfaces, just a stack of planes, all parallel to the sheet itself. Nice and uniform.
All right, so now we know the basic shapes. But there's a really specific relationship between these surfaces and the actual electric field lines. There are 2 fundamental rules here that you absolutely have to know, and they govern how these 2 things interact.
So here are the 2 big, non-negotiable rules. Rule number 1, electric field lines always cross equipotential surfaces at a perfect 90-degree angle. They're always perpendicular. And rule number 2, the electric field always points downhill. That is, from a place of high potential to a place of low potential. It's exactly like gravity. A ball is always going to roll down the steepest part of a hill, right? Perpendicular to the contour lines. Same idea here.
Now, in the absolute simplest case, remember those parallel planes we just saw? The math is super straightforward. The difference in potential between 2 of those planes is just the strength of the electric field, which we call E, times the distance between them, which we call D.
But life isn't always that simple, right? What happens if things aren't lined up so perfectly? Well, that's where this, let's call it the master formula, comes into play. This is the key that lets us turn our map into an actual measuring tool. It has that little bit about the angle in there, which lets us figure out the electric field no matter how we're measuring it.
Okay, theory time is over. We've got the concepts, we've got the formula. Let's put this into practice and actually use a map to measure something invisible.
So here is our challenge. We have this equipotential map. We can see 3 lines, one at 10 volts, one at 20, and one at 30.
We're given a distance and an angle. And the question is, just using this picture, can we figure out the exact strength and direction of the electric field here? And the answer is a big yes.
It's actually pretty easy if we break it down into 3 steps. Step 1, find the potential difference, or delta V. Let's just pick the 20-volt and 10-volt lines. The difference? Easy, 10 volts. Step 2, we need to find the shortest perpendicular distance between those lines. Now the map gives us a horizontal distance and an angle, so we just use a little bit of high school trig to find the true D. And finally, step 3, we just plug our numbers into the formula. The electric field is just that potential difference we found divided by the perpendicular distance we just calculated. And when you run those numbers through the calculator, what do you get? You get 400 volts per meter. And just like that, we did it. Think about what just happened. We took a simple 2D map, and we used it to measure the strength of an invisible force. Now that is pretty cool.
All right, for our last section, I want to show you something really fascinating and honestly a little weird. It's the case of a charged, hollow sphere. What happens on the inside of one of these things is probably not what you'd expect.
Okay, don't get hung up on the equations here, just look at the graphs. On the left, you see what happens outside the sphere. The potential gets weaker the farther you go. Totally normal, what we'd expect. But look at the graph on the right, which shows what's happening inside the sphere. The line goes completely flat. The potential just stops changing. It's constant everywhere inside.
This is a really fundamental principle of physics. The second you move inside any charged hollow conductor, the electric potential becomes uniform. It's the same everywhere. Every single point inside has the exact same potential as the surface. It's kind of like walking into a building where every single room, no matter where you go, is on the ground floor.
So who cares, right? Why does this matter? Well, this is the entire principle behind something called electrostatic shielding, a Faraday cage. By putting sensitive electronics inside a metal box, which is just a hollow conductor, you create a zone where the potential is constant. And that zone acts like a shield, protecting all the delicate stuff inside from any crazy electric fields on the outside. This is used everywhere. In your microwave, in high-tech cables, it's a huge deal.
And that brings us to one last question to leave you with. We've established that an electric field is basically like a slope, right? It only exists when there's a change in potential. So if the potential inside that hollow sphere is completely flat, completely constant, what does that tell you about the electric field inside of it? I'll let you think about that one. The answer is the whole reason shielding works in the first place.